Have you ever tried to imagine a world that never cools down? Picture a small, sun-scoured globe, surface bright as hammered metal, shadows colder than deep space. Craters overlap like fingerprints of time. Noon is brutal, night is airless. This is Mercury first in line, last to keep an atmosphere, and still full of questions. Why does a tiny planet hold a giant iron core? How does a magnetic field survive so close to the sun? What do cliffs the size of states say about a world that shrank as it hardened? We'll keep the pace steady. Simple facts, clear steps, no drama. If this kind of calm exploration fits your style, a quiet like and subscribe helps others find it. Settle in. Let's see how silence behaves at the edge of daylight. A small planet so close to the sun should be dry and simple. Yet Mercury holds permanent ice in deep polar craters. These craters sit near the poles where sunlight never reaches the floors. Temperatures there stay far below freezing, while nearby ground bakes. The same world gives both extremes, because there is almost no air to move heat around. Daytime surfaces can exceed the melting point of lead. Nights plunge to bitter cold. Mercury is the smallest planet, but its core is unusually large and metallic. It goes around the sun in 88 days, but a full day from sunrise to sunrise takes 176 Earth days because of the way it spins and orbits together. It is a quiet place of sharp light and deep shadow. It is also one of our closest neighbors, and still one of the least understood. Many people skip over it while looking at rings, storms, and giant moons. But Mercury holds clear records of early solar system events. Its story is written in impact scars, collapsed cliffs, and the timing of its odd rotation. We can read that story if we move slowly and keep the sequence of facts straight. Ancient watchers noticed how briefly it appears. Mercury rises just before dawn or sets just after dusk, never far from the Sunday. It was named for fast gods and for keepers of writing, because following it requires careful notes. The Romans called it Mercury, the quick messenger. The Greeks linked it with Hermes, the guide and boundary crosser. In Mesopotamia, it was Nabu, patron of scribes. In Egypt, it was tied to Thoth, the counter of time. In India, it is Buddha, a name that still marks Wednesday in many languages. In Chinese tradition, it is the water star, connected with the element of flexible motion. These labels share a theme: speed, record keeping, and skill with timing. Those skills were useful because the planet seemed to live two lives. People at first thought the bright point in the morning and the one in the evening were different objects. Careful tracking showed they were the same. Mercury orbits inside Earth's path, so we only see it in the short windows of twilight. As it rounds the sun, it switches sides in our sky, attending sunrise for a season, then sunset for the next. That pattern also explains why it never gets high above the horizon. Geometry matters. In late winter and spring evenings for northern observers, the path of the sun and planets the ecliptic stands steeply from the western horizon, giving Mercury a better angle. In the opposite season, the eastern morning sky gives it the lift. When the angle is shallow, the view is poor, and air close to the horizon shakes the image. Telescopes reveal phases like a small Venus, crescent, half, and gibbous. That was strong evidence that Mercury orbits closer to the sun than Earth does. Yet the surface stayed hard to map because we usually view through thick, unsteady air. Early charts guessed at dark patches, but the drawings disagreed. In the 1800s, many astronomers thought Mercury kept the same face toward the sun, turning once per year in a locked state, the way our moon keeps one face toward Earth. This idea fit the data they had, but was not correct. In the 1,960 seconds, radar signals bounced off Mercury showed a different rhythm. The planet turns 3 times for every 2 trips around the Sunday. This is a 3-to-2 spin-orbit resonance. It makes daytime at a given location very long without being endless. The path of Mercury around the Sun also held a clue. Its orbit is an ellipse, and the closest point to the Sun, called perihelion, shifts slowly over time. Most of the shift comes from the pull of other planets, but a small leftover drift remained that Newton's gravity could not account for. People searched for a hidden inner planet, Vulcan, to explain the extra pull. No such planet was found. In 1915, general relativity solved the mismatch. Space and time curve near the Sun enough to advance Mercury's perihelion by the missing amount. The smallest planet helped confirm a large idea about gravity. Up close, Mercury shows heavy damage from ancient impacts. The Caloris Basin is one of the largest impact structures in the solar system. The strike that made it lifted rings of mountains and sent shockwaves through the planet's crust. On the opposite side of the globe, a strange, jumbled terrain likely formed where those waves focused. Beyond the big basin, craters overlap in dense layers, marking a surface that has not been erased by weather or plate motion. There are also long cliffs called scarps. They look like curved, step-like walls hundreds of kilometers long and up to a few kilometers high. These scarps formed as the planet cooled and shrank. The outer rock wrinkled as the interior contracted. This tells us the planet lost enough internal heat to literally crumple. Polar regions add another layer. Radar from Earth and from spacecraft saw bright, reflective patches inside shadowed craters near the poles. The best explanation is water ice mixed with dust, protected by permanent shade. Even so close to the Sun, those pockets stay cold enough to keep ice stable for long periods. The rest of the surface offers no such shelter. Inside, Mercury is dominated by a large iron core that likely takes up more than half its volume. Several ideas could explain this. Early Mercury may have lost much of its lighter rock in a giant impact. Or the hot young Sun may have driven off lighter materials near its heat. Regardless of the path, the result is a metal-rich world with a thin, rocky shell. Despite its small size, the core is not fully solid. Enough liquid remains to power a weak magnetic field. This was a surprise when first measured. Since small bodies usually cool and freeze solid, Mercury's field is much weaker than Earth's but real, and its shape suggests the core is offset slightly from the planet's center. Our direct knowledge comes from a few missions. Mariner 10 flew by in the 1,970 seconds and imaged less than half the surface, but it proved that a magnetic field exists. Decades later, the Messenger spacecraft went into orbit and mapped nearly all of Mercury in detail. It measured the elements on the surface, the shape of the gravity field, and the structure of the magnetic field. It found evidence of recent, small-scale tectonic activity and supported the case for polar ice. The next step is Bepi-Colombo, a joint mission now cruising with gravity assists. When it enters orbit, it will provide complementary instruments to refine maps, fields, and composition. Small, careful facts give a coherent picture. Mercury is airless, extreme, and metal-rich. Its rotation is locked into a 3-to-2 resonance. Its orbit precesses in a way that matches general relativity. Its surface holds scars from the earliest times and cliffs that prove global shrinkage. Its poles trap ice in eternal shade. Its core still moves enough to create a magnetic field. Each point is testable. and has been measured. Mercury sometimes writes a neat mark on the Sunday, when Earth, Mercury, and the Sun line up. The planet crosses our view as a tiny dark dot. That pass is a transit. It sounds simple, yet it asks for careful filters and careful timing. The first telescopic transit in the 1600s was more than a sight. It was proof that precise orbits and good predictions match the sky. One moving shadow fixed a whole world in place. Not every odd motion is so rare. At other times, Mercury only seems to misbehave. We and Mercury travel at different speeds, on paths around the Sunday. From our moving vantage, the faster inner planet can appear to slow, stop, and drift backward against the stars for a short stretch. That is retrograde motion. Nothing actually turns around. It is the same effect you notice when your train passes a slower one and the other cars look like they slide the wrong way while both trains keep going. The sky builds that platform trick into its view. Missed messages and lost keys start with us, not with a small airless planet keeping to its regular path. Before telescopes, observers turned this motion into a practical skill. You learned where to look and when. Mercury hides near the sun's path, so you watched the west after sunset or the east before sunrise, depending on the season. You learned that it brightens as the sky darkens, then fades quickly into the glow. You taught students to use averted vision, letting the edges of the eye find faint objects first, and only then fixing the gaze. You accepted that predictability lives inside short windows and that many people never notice the planet at all. The old names stayed as gentle prompts to pay attention. Hermes crossing borders, Nabu and Thoth keeping records, Buddha as quick mind, the water star as a symbol of flow in time. They are images, but they match the task. You need speed, notes, and patience to follow this world. Numbers give the frame. Mercury never strays far from the sun. Its greatest elongation is only a few tens of degrees. Its evening to morning cycle averages about 116 days. Its year is 88 days. The names remind you how to feel the search. A threshold object, seen near the edge of light, with a low western horizon on the right evening, you can take part in a very old routine. Wait until the sky turns deep blue. If Venus is up, use it as a guidepost. Look a bit below and to one side of the sunset point. When a small, steady point declares itself, you have found a planet and a practice. For a few minutes, you share the same calm result that early watchers stored on clay. Memory is your record, and you can repeat the sight at the next dawn if you like. Mercury moves fast, yet the act of watching it is slow. The orbit explains the speed. Mercury completes a trip around the sun in 88 days. Close to the sun means deep in the sun's gravity well. To stay in orbit, the planet must move quickly, tens of kilometers per second. The path is not a perfect circle. It is an ellipse, a stretched loop. Distance and speed change through the year. Faster and hotter near perihelion, slower and cooler near aphelion. That variation shapes what a day feels like on the ground. Spin adds the second part. For years, many thought Mercury kept the same face to the sun, like our moon keeps one face to Earth. Radar in the 1960 seconds showed a different pattern, a 3-to-2 spin-orbit resonance. The planet turns 3 times on its axis for every 2 trips around the Sunday. Tides and internal friction push a body toward a simple lock, but the odd shape of the orbit changes the torques. Over long time, the system settled into this ratio, because it sheds the least energy. The result for timekeeping is unusual. A sidereal day, the spin period relative to the stars, is different from a solar day, the time from one noon to the next. On Mercury, the solar day lasts 176 Earth days. The planet with the shortest year has a noon to noon longer than 2 of its years. Eccentricity adds an extra twist to the sky. As Mercury falls toward perihelion, it speeds up on its track. In some longitudes, that faster orbital motion briefly overtakes the steady spin. To an observer, the sun near the meridian can slow, stop, drift backward a little, pause again, and resume forward motion. Sunrise can stall on the horizon before committing to day. The same pause can happen near sunset. 2 broad regions, roughly opposite each other, feel this effect most strongly. Geometry picks them out, where the resonance and the changing orbital speed line up. Senses on the surface would register a different world. With no air, the sky is black at noon and stars are visible. The sun looks large. Dawn is slow. Light climbs crater rims and pours down walls over many Earth days. Shadows move like a clock hand you can barely see. Rock in sunlight heats hard. Rock in darkness radiates heat away into space. Without wind, there is no easy exchange between the two. The border between hot and cold is set by landforms and by the sun's crawl. A single step from shade into light would feel like a switch. The long day also means a long time for materials to crack, fuse, and change near the surface. The resonance leaves a faint long-term mark. The same longitudes receive the most intense sunlight at or near perihelion every other Mercurian year. Over millions of cycles, repeated heating and cooling may alter surface properties in those belts, compared with regions that reach noon when the planet is farther from the sunday. Spacecraft maps show differences in reflectivity and chemistry across planes. Impacts and old volcanic flows explain much of the pattern, but the steady thermal rhythm likely adds its own quiet effect. It is natural to test living logistics in thought. One idea is to ride the terminator, the line between night and day, to stay in the mildest band of temperature. On Mercury, the terminator creeps very slowly. In theory, a habitat could move at walking speed to hold constant dawn or dusk. In practice, the line crosses crater rims, rubble fields, and steep scarps. There are no roads. A more workable approach would be fixed sites at high latitudes, cut into crater walls, where the sun skims low and shade can be built. In any case, the 3-to-2 schedule sets the clock and demands long planning. The orbit carries an older riddle, the precession of the perihelion. Mercury's ellipse rotates slowly within the orbital plane, so the closest point to the Sun advances over time. Most of that advance comes from the pull of other planets and small effects like the Sun's slight oblateness. When 19th century astronomers added all Newtonian contributions, a small leftover remained, about 43 arcseconds per century. The angle is tiny, but it was measured and confirmed. Explanations bloomed and faded. A hidden planet called Vulcan, dust rings, tweaks to gravity. None held up. In 1915, general relativity supplied the missing piece. Mass and energy curve spacetime. Planets follow geodesics, the straightest paths available in that curved geometry. Near the Sun, the curvature is strong enough to advance Mercury's perihelion by exactly the observed amount. The success mattered because it turned a mismatch into a necessary result. Today, the correction is standard in navigation. Mission planners include it when they compute trajectories. Radio scientists include it when they time signals. The equations and the world match to high precision. Relativity does not change daily life on the surface, but it shapes the tables people use to aim a spacecraft. In that sense, Mercury is both an object and a test. A small planet near a star quietly checks a theory about gravity every time it rounds perihelion. From far away, Mercury looks like the Moon, grey, cratered, and old. Both worlds are airless. Both keep their marks because there is no rain, no rivers, and no plants to erase them. The likeness ends when you read the details. Mercury's crust sits above a huge metal core, so density and stresses differ. Wide plains in many regions are smoother than common lunar fields. The surface tells a story of heavy bombardment mixed with calm, widespread lava that has long since cooled. On an airless body, impacts are the default machine. Meteoroids and asteroids arrive at high speed. Their energy turns to heat and pressure in a blink, carving bowls and throwing out debris. Small craters are simple, sharp rims and blankets of ejecta. Larger ones bounce the crust and raise central peaks. The largest form peak ring basins, where a ring of mountains stands inside the rim. Mercury holds every scale, from small pits to the Caloris Basin, which stretches across a large part of a hemisphere. With no weather to blur edges, age shows in shape. Sharp rims mean young. Softened rims cut by later strikes and splashed by secondary craters mark old. Between scars, plains fill the lowlands. Seen from orbit, two textures repeat. Intercrater plains are very old surfaces, crowded with overlapping small craters. Stand there, and the horizon would undulate with low, pitted ground, like hammered metal. These regions likely formed early, when impacts were so frequent that debris and melts welded into a rough fabric. In some places, the surface looks near saturation, where each new crater partly erases another. Smooth plains form Mercury's second major texture. These broad, flat sheets fill basins and drape older terrain, gleaming under low sunday. For a long time, their origin was debated. Are they mostly impact melts spilled from giant basins, or true lava flows? High-resolution mapping and compositional data point to volcanism in many regions. Subtle flow fronts, levees, and distinct chemistry mark plains that spread across lowlands. Inside basins like Caloris, their color and composition differ from surrounding highlands, a hint that the material rose from depth rather than being a simple remix of the surface. Early Mercury was not a quiet surface under fire. It was a surface rebuilt. Impacts scarred the crust, while interior heat sent magma upward to bury those scars. From orbit, the boundaries between rough, older ground and younger smooth sheets can be sharp lava ponded cleanly in lows or gradual where flows climbed and thinned against higher rims. Across many plains run broad, low folds called wrinkle ridges. Like frozen waves, they form when wide areas are gently squeezed after the lavas cool and contract. The pattern scales up to the whole planet. As Mercury's interior lost heat and shrank, the outer shell took up the slack by wrinkling and thrusting, leaving ridges on the plains and long lobate scarps across the landscape. Craters come in families that help tell time. Fresh craters with bright rays stand out. Rays are streaks of ejected dust and blocks that can extend for hundreds of kilometers. Far from the main crater, chains of smaller pits mark where fragments fell back in graceful arcs. As years pass, rays darken, edges soften, tiny micrometeorites chip away at grains. New impacts pepper the pattern. On Mercury, space weathering also changes the surface. The solar wind and steady dust impacts can remove some easy-to-evaporate elements and darken or lighten patches. Subtle color differences, too faint to see by eye, but clear in calibrated images, mark places with different histories and chemistry. Sharpness gives a first guess at age, color, and composition. Add detail. Stand in imagination on an intercrater plane and you feel age. The ground looks like hammered metal, low and pitted. Overlapping bowls merge until circles become polygons. It is an old surface, built by many small strikes. By contrast, smooth plains feel younger. They wrap around older hills, bury parts of rims, and in some spots leave only ghost rings peeking through as faint ridges. Where a smooth plain enters a basin through a gap, you can trace its path, guided by slope the way water would flow on Earth. Except here the flow was lava under a black sky. Mercury resembles the Moon in color and in the number of craters, but the differences matter. Gravity is stronger on Mercury, and the crust and mantle have a different mix of elements. That changes how impacts behave. The sizes at which central peaks and peak rings form shift. Many smooth plains on Mercury are broader than lava seas in similar basins on the Moon. The small planet had a surprisingly active volcanic phase. Cutting across both old and young ground are lobate scarps, long, curved cliffs that step the terrain down. These are the clearest signs that the planet shrank. Scarps slice smooth plains like the lifted edge of a rug. Elsewhere, they run through old craters and offset rims, turning circles into chords. Each crosscut fixes order, impact, then lava, then faulting or sometimes a different order, where the lines show another sequence. Some bright patches stand out on crater floors, rims, and along contacts between smooth and rough terrains. They are not just sunlit slopes. They have distinct reflectance and color, and often sit near shallow, rimless depressions called hollows. Hollows likely form when certain elements near the surface are lost to space, leaving behind collapsed pits and bright debris. Their locations show that the surface still changes on small scales. Chemistry remains active enough, under extreme heat and cold, to keep carving fresh features on very old ground. With no air to carry dust far, roughness and tone stay local. Each impact throws out its own apron of debris. On rugged intercrater plains, the blanket adds roughness to roughness. On smooth plains, it pebbles the sheen and marks boundaries that become most obvious when the sun is low. Lighting matters. High sun emphasizes color and composition. Low sun emphasizes shadows and height. Images under different light tell different truths. Reading a single high-quality image, you can stack events like layers. A smooth plane that buries half a crater rim must be younger than the impact that made the rim. A field of densely overlapped small craters points to a time of heavy bombardment. A bright ray system that crosses both rough and smooth ground is younger than everything it crosses. A scarp that kinks a ray is younger than that ray. Using such overlaps and crosscuts, you can build a sequence. Bombardment, volcanism, contraction, repeated in places at different scales. Compared with Earth, Mercury's way of keeping records is direct. Earth's plates move, seas fill basins with sediment, mountains rise and wear down, and weather hides and reshapes the land. On Mercury, there is no rain, no wind, and no plant cover. Memory remains by default. The angle of light is your filing system. Crater density is your index. Two main textures dominate: intercrater plains old and rough, and smooth plains, younger and more even. Along many boundaries, lava once spilled over rims and froze into rounded ledges. In other cases, it flowed around older hills, leaving a moat that maps the older topography as a negative. Even small, fresh craters can create miniature smooth patches when their impact melts pool and cool as glossy sheets. The small echoes the large. Mercury's surface is straightforward in this way. What you see is close to what is there. Clouds do not hide shapes. Forests do not cover slopes. Waves do not redraw edges. Craters, plains, scarps, and the lines between them hold their places and change slowly under micrometeorite rain. The moon shows a similar honesty, but Mercury adds its own patterns: thicker volcanic sheets in some basins, grander global scarps, and chemical signatures tied to a large iron core. One feature organizes much of the planet's face: the Caloris Basin. It is a very large impact basin, about 1,550 kilometers across, framed by rings of mountains and surrounded by ridged, grooved ground. Parts of its interior are covered by light-toned, smooth plains. Outside the rim, the surface is drawn into long, lineated patterns that extend for hundreds of kilometers. Caloris formed in an instant from a high-speed strike by a body several tens of kilometers wide. The impact released energy that melted and vaporized rock. A deep cavity opened. The crust rebounded, collapsed, and rebounded again. Concentric rings formed as layers moved like nested springs. Debris flew out on ballistic arcs and fell as thick sheets. Some of that debris slid while still hot and made the lineated aprons beyond the rim. What remains is a multi-ring basin, a kind of bullseye in rock. The rings, called the Caloris Montes, are not one continuous wall, but chains of rugged peaks. Between rings, terraces, and ridges record how the crust settled. Outside, grooves and ridges align with the basin, like ripples around a stone dropped in water. The pattern reflects the physics. Shallow layers were launched outward and redeposited. Deeper layers slumped inward. Inside the basin, time added new material. Much of the floor is covered by smooth plains whose color and chemistry differ from surrounding highlands. For years, the debate was whether these plains are mainly impact melt or later volcanic sheets. Close inspection favors volcanism for many areas: subtle flow fronts, embayments against older hills, and compositions point to lava that rose from depth rather than only melted crust. The impact did not just carve, it opened pathways. Heat and fractures let magma reach the surface and pave the floor. A striking interior feature is a web of troughs called Pantheon Fossae. From above, it looks like spokes on a wheel. Narrow, shallow grooves radiate from a central region. Near that center lies Apollodorus, a bright-rimmed depression that may be a volcanic vent or an impact scar later modified by tectonics. The geometry reflects stress. As the plains cooled, as the basin adjusted to loads, and as the planet continued to contract, the crust cracked in repeated patterns. The troughs are the map of that strain. Caloris is old. Many studies place its formation near the tail end of the heavy bombardment, roughly 3.8 to 3.9 billion years ago, when leftover building blocks still roamed the inner solar system. Its age and its clear state make it valuable. On Earth, a basin like Caloris would be destroyed or hidden by plate motion and erosion. On Mercury, it endured. It holds in one place the marks of the impact, the record of volcanic resurfacing, and the later cuts of contraction. It is a compact lesson in how a rocky world responds to a single great event and to long cooling afterward. Follow the great circle around the globe to the point opposite Calorus, the antipode, and you find a very different but related scene called the Weird Terrain. It is a field of jumbled hills and tilted blocks. Valleys twist, slopes meet at odd angles. The area lacks a central crater to explain the disorder. The leading idea uses how waves behave in spheres. An impact sends shock waves not only along the surface but also through the interior. On a sphere, those waves spread and refocus at the opposite point. The Calorus impact likely sent deep waves that met at the antipode and broke the crust there, lifting and shattering it. Debris from the impact may also have fallen on the area, adding a coarse layer that increased relief. The result is a landscape shaped by energy delivered from far away. It is an elegant effect. One strike, two linked terrains, rings and plains at the source, broken ground at the far side. Other bodies show similar echoes. Some lunar basins have antipodal disturbances. Mercury's example is especially clear because of the scale of Calorus and the strength of the pattern. The pair is useful for teaching. A single mosaic showing the basin and its antipode can explain focused shocks without a formula. Calorus also helps set the timeline for other features. Where a bright ray from a younger crater crosses lava inside the basin, the order is clear. Basin, then lava, then the young crater. Where a lobate scarp cuts the smooth basin floor, the scarp is younger than the lava it offsets. Such cross-relations make Calorus a timekeeper. Its features slice across or lie on top of others, letting geologists build a more detailed history than crater counts alone would allow. Even the color differences matter. Lava inside Calorus often shows a distinct hue compared with older highlands. That suggests a different chemical mix, pointing to magmas drawn from deeper sources. The basin therefore opened not only a hole, but also a window into the planet's interior. How much it had separated into layers, how much heat remained, and how long magma could still rise to the surface. Imagine standing near the rim. You would not see a smooth circular wall. You would see belts of mountains, broken and jagged, their edges cut by later impacts, their profiles sharp against a black noon sky. Underfoot, the ground would be a mix of breccia rock fragments welded by heat and larger intact blocks. In places, later lava would have crept up to the base of the hills and cooled as smooth patches. Walk inward, and the floor changes from rough to smooth, from impact architecture to volcanic paving. Follow one of the troughs of Pantheon fossae, and you would move along a shallow groove that narrows and then fades, defined as much by shadow as by slope. At the antipode, the mood changes. The hills look piled, the gaps between them wander, and there is no obvious central crater. That absence is a clue. The energy came from the other side. From a planet-wide view, the line between Calorus and the antipode is clear. Strike here, echo there. The pattern ties two distant regions into one event. Outside the basin, its influence still shows. Long lineations radiate from the rim. Ejecta sheets drape older ground. Fine details matter for reading time. A ray that crosses a scarp dates the ray after the faulting. A scarp that offsets a ray dates the scarp after the impact that made the ray. Color differences that follow topography argue for lava flows. Color patches that ignore slope can point to composition differences set by impact melts or by later chemical changes. Each clue narrows the sequence. Because Calorus is so large and so well preserved, It serves as a reference. Beyond age and order, it also hints at how Mercury's interior behaved. Lava inside the basin is not just remelted local crust. It carries its own chemistry. That means heat and materials from depth were involved long after the impact. The interior stayed warm enough and connected enough by fractures to feed eruptions. The basin did not only cool, it evolved. Walk the rim in your mind and cross inward. Fractured mountains give way to smoother floors, then to patterned troughs that record how the basin settled and cooled. Trace a line to the far side of the planet, and you meet its echo at the antipode, a field of jumbled hills where focused shockwaves broke the crust. Step back to an orbital view, and both scenes connect. One impact teaches many lessons at once: how rock flows under shock, how lava later resurfaces lowlands, how slow cooling tightens the shell, and how energy moves through stone over long spans. From that broad frame, the story returns to a repeating mark written almost everywhere. Long, curved cliffs break and step the plains and highlands alike. These lobate scarps cross old craters and young volcanic sheets, cutting what came before and fixing the order of events. Their arcs and offsets let geologists measure how much Mercury has shortened since its crust hardened. They are the creases that make time legible. Lobate scarps are more than scenery. They are thrust faults, places where one slab of crust rode up over another because the planet had to fit into a slightly smaller shape. The reasoning is straightforward. Rocky worlds begin hot. Early collisions add heat. Radioactive elements supply heat for ages, and a large metal core keeps warmth the way a heavy pan holds heat after the stove is off. Over billions of years, that heat leaks to space. The deep interior contracts as it cools. Without plate tectonics to slide and recycle the surface, the outer shell must shorten to match the smaller interior. Mercury, small and metal-rich, shows the effect cleanly as global compression and a web of scarps that run for hundreds of kilometers and rise hundreds of meters, sometimes more than a kilometer. Under low sun, their shadows draw sharp lines, and their shapes are easy to read. A planet-wide ledger of how an iron heart slowly tightened the skin. Their order in time is readable with simple rules. A scarp that cuts across the rim of an old crater and offsets the circle must be younger than the crater. A scarp that steps down a smooth lava plain with a fresh apron of debris at its base is younger than the lava. Patterns like these show that compression did not happen in a single episode. It continued as a slow tightening, late enough to deform even some of the younger planes. The sequence becomes a ledger: basin, then lava, then fault, or in some localities, a reversed order that records local changes in stress through time. Mercury likely shrank more than other rocky worlds because of its unusual build. It is the smallest planet, but has an outsized iron core that takes up most of its volume. When so much of a planet is metal, even a small percentage of cooling and contraction in the core becomes a large absolute change in size. The rocky shell above is comparatively thin. Without plates to move sideways, it had to crumple. Crumpling became thrusting. Thrusting became scarps. Mercury's location and origin may have amplified the effect. Close to the Sun, it may have formed with fewer light elements. It might also have been struck early by a giant impact that stripped away part of its rocky mantle, leaving the metal-rich interior dominant. Whatever the exact recipe, the result was a planet that kept heat in its center, yet cooled enough at its edges to contract. Daily tidal flexing from the Sun's gravity also needs the interior and helps dissipate energy over long spans, adding to the tendency to wrinkle. Picture standing only in thought on the crest of one of these cliffs. The upthrown block would be a rounded back slope underfoot. Ahead, the ground would drop in a clean step to a lower plane. At the base, broken blocks would form a wedge of rubble. Follow the trace of the scarp and it bends and snakes across the landscape, ducking under younger deposits and reappearing like a buried rope. Where several scarps run roughly parallel, the plane looks pleated. Each fold changes tone with the sun's angle. It is geology in a quiet key. No steam, no storms, just rock taking up strain over time. Comparisons help. The moon has lobate scarps too, evidence of cooling and contraction, but they are fewer and generally smaller. Earth hides global contraction by letting plates drift, collide, and dive back into the mantle. Our shortening becomes mountain belts at plate boundaries rather than planet-spanning thrusts that cross old landforms. Mercury has no plate edges to channel stress. The shell buckled where it needed to, often in long arcs that ignore crater rims and lava fronts, except to offset them as it crosses. Images show a scarp turning a once round rim into two slightly shifted arcs, the way a pressed coin shows a slip along its edge. The net shrinkage sounds modest as a number, but is large for a whole world. Mercury's radius has dropped by a few kilometers since its outer shell hardened. That is enough to wrinkle a sphere. A useful picture is a hard-boiled egg cooling. The inside contracts, and the shell cracks and overlaps in small steps. Lobate scarps are those overlaps, scaled up. When higher resolution mapping arrived, the count of scarps grew. From their spacing and sizes, scientists estimate how much horizontal shortening took place. These cliffs are more than scenery. They are clues to the interior. Close spacing and low relief point to a thinner, warmer lithosphere at the time of faulting. Wide spacing and taller throws point to a thicker, stronger shell. By tying scarp patterns to ages from crater counts, we can trace how the lithosphere thickened as the planet cooled. Cooling links to another key fact. Mercury has a magnetic field. Weak, but real. A magnetic field like this needs a moving, electrically conducting liquid in the core, a dynamo. Young-looking scarps, sitting on top of relatively fresh plains, together with the presence of a field, imply a planet doing two things at once: stiffening at the surface while its deep core still circulates metal enough to wind and maintain magnetic lines. Cooling tightens the skin while the heart continues to stir. Scarps also reveal how different materials respond to the same push. Crossing an old intercrater plane, a scarp may be jagged, with many small breaks where buried blocks steer the fault line. Crossing a younger, more uniform lava sheet, the same scarp may draw a smoother path. In some places, instead of one sharp fault, the surface flexes into a low wrinkle ridge, a ductile fold where strain is spread through a thick layer. Such contrasts help separate regions that are debris-rich from those that are lava-rich. They also hint at past temperature differences. Warmer, softer rock tends to fold. Colder, stronger rock tends to break. These links fit together neatly. The oversized core explains the scale of contraction. Contraction explains the prevalence and reach of the scarps. The scarps give timing for cooling. The cooling story supports a working core dynamo, and the dynamo shows the interior has not frozen solid. Mercury's iron heart still moves enough to matter. The light makes these structures easy to study. At low sun, their shadows draw lines like ink. At high sun, the lines fade and other textures stand out. During Mercury's very long dawns and dusks, The shape of each scarp emerges and recedes with steady clarity. Small craters on a scarp's face add another layer of timing. Faulting did not erase the surface. Impacts continued to arrive and layer new marks onto old faults. A rim cut by a scarp or a ray kinked by a scarp pins the order at that spot. Each intersection is a timestamp. Mercury's thermal environment frames how all of this looks and lasts. On Mercury, sunrise accumulates. There is no air to scatter light, so the sky stays black, even at noon. The sun grows large near perihelion and smaller near aphelion, but it always moves against a field of stars. Because there is almost no atmosphere, heat moves mainly by radiation and by slow conduction within rock. In sunlight, the ground absorbs energy and glows in infrared until it reaches balance. In darkness, it radiates away its stored heat unchecked. A single boulder can mark both extremes at once. Its sun-facing side hot enough to soften many materials, its shaded side bitter cold. Time stretches the contrast. A solar day on Mercury, noon to noon, lasts 176 Earth days. Dawn can take weeks as light slides across crater rims. The top few centimeters of rock swing the most in temperature. Deeper layers lag. A thin overhang can cast a ribbon of shade that matters. Without air, the boundary between hot and cold is drawn by shape. Every boulder throws a private night behind it. The terminator, the line between day and night, moves slowly. In theory, a moving shelter could keep pace with that line and remain in mild temperatures. In practice, the ground is broken. Crater rims, talus, and ridges do not offer easy paths. The poles present a different regime. Mercury's axis is tilted by only a tiny amount, so the sun skims very low above polar horizons. Floors of some polar craters lie so deep that sunlight never touches them. These permanently shadowed regions are colder than any sunlit surface on Earth and stay cold for millions of years. In such conditions, volatile substances that would otherwise escape can collect and persist. Earth-based radar first hinted at bright, reflective patches in these shadows, with signatures consistent with clean, coarse ice. The bright spots matched locations that should be permanently dark. Spacecraft data strengthened the case. A laser altimeter mapped polar crater shapes and confirmed which floors never see sunlight. A neutron spectrometer looked for hydrogen by measuring how cosmic rays make neutrons in the soil and how those neutrons lose energy when hydrogen is present. Where radar said bright, the neutron instrument said hydrogen-rich, and the altitude data said always dark. In some places, near-surface layers tens of centimeters thick appeared to be water ice. In others, a darker cap a few decimeters thick may cover brighter ice below. The cap could be organic-rich material cooked by radiation into a dark rind that helps insulate the ice. Delivery and migration explain how ice arrived. Comets and some asteroids carry water and other volatiles. When they strike Mercury, some fraction of that material is vaporized and lofted. On an airless world, molecules move in hops. They fly on ballistic arcs, land, and may be kicked off again by heat or light until they either escape or fall into a cold trap. Permanent shadows at high latitudes are the deepest traps. Over long time, a slow rain of molecules from impacts and from the breakdown of water-bearing minerals can fill those sinks. The pattern is patchy later impacts, and small slides can bury or expose ice, but the overall result is a migration of water to the coldest places. The polar deposits differ from place to place. Some bright patches look like nearly pure surface ice. Others are buried and hidden under dark mantles. The dark cover reduces heating from stray, scattered light and from warm slopes nearby. The presence of ice at Mercury's poles is more than a curiosity. It connects with similar cold traps on the Moon. It shows how water can move and settle on bodies without air. It provides a natural freezer where ancient material can remain stable. Far from the poles, heat and radiation change the surface slowly. Over time, sunlight and the solar wind drive off more volatile elements from the top grains and alter their optical properties. That ongoing distillation can change brightness and color and may help form the shallow, rimless pits called hollows. Hollows are often surrounded by bright, fresh-looking material. They may form where heat and radiation remove certain elements and cause the surface to cave slightly. They appear in many settings, sometimes cutting into smooth plains and sometimes into older rough ground, which shows that local chemistry still matters. The extremes set engineering possibilities. Sunlit slopes near the poles can provide steady power. Nearby shadowed floors can hold cold supplies. A site carved into a polar crater wall could place solar arrays on a ridge with near constant light while using deep shade for storage. On the equator, small overhangs and boulders can create local pockets with reduced heat loads. Even a light-toned boulder that reflects more sunlight could act as a simple radiator for what sits behind it. Mercury is harsh in averages but rich in edges, and edges can be used. Temperatures set the scale. In full high sun, the surface can top 400 degrees Celsius. In deep shadow, it can drop below 170 degrees Celsius. Those extremes stress ordinary alloys and make many materials brittle. Hardware and procedures must work for both. The same ground that could soften a solder might one step away keep water ice stable for geologic time. The reasons are geometric, not weather. Heat arrives only as radiation. Cold is simply the absence of that radiation, not a gust of air. With almost no axial tilt, the sun skims the polar horizons and never reaches some crater floors, so those pockets act as freezers. Near the equator, days are long and nothing convects heat away. Rock and dust, not air, set the pace of warming and cooling. The terminator creeps. Long day and long night let surfaces settle deeply into hot and cold. Across this thermal stage, lobate scarps keep their sharp edges lines cut by stress and preserved by stillness. That stillness has a cause. Mercury has no true atmosphere to move, sound, or spread heat. Above the ground lies an exosphere so thin that atoms rarely collide. Each particle travels alone, arcs, and either falls back or escapes. A cubic meter of this air holds fewer atoms than a high-grade laboratory vacuum. Space, in practice, begins a short step above the surface. This exosphere is made and unmade all the time. Sunlight, heat, the solar wind, and micrometeoroids all knock atoms free from the top layer of rock. Three steady processes dominate. In photon-stimulated desorption, light kicks loosely bound atoms off grain surfaces. In thermal desorption, heat, during the long day, bakes atoms free. In sputtering, fast-charged particles from the solar wind slam into the ground and blast atoms out, like sandblasting on a microscopic scale. Tiny impacts add brief plumes by vaporizing a dusting of soil. None of these make weather. They make a thin, shifting fringe. Sodium and potassium stand out, with calcium and magnesium also present. Hydrogen and helium are there too, but most of those come from the solar wind rather than the crust. Sodium is the easiest to spot. Sunlight excites sodium at its yellow wavelengths. Radiation pressure then nudges those atoms away from the Sunday. The result is a faint sodium tail that can stretch millions of kilometers behind Mercury. It is invisible to normal sight, but shows up in narrow filters from Earth. In such images, the smallest planet wears a ghostly fan like a tiny comet, its exosphere blown downwind. Because atoms do not collide much, the exosphere has seasons that are set by geometry, not by weather. Near perihelion, sunlight and radiation pressure are stronger. The surface is hotter, and sputtering is more vigorous in some regions. Sodium clouds grow, and the tail brightens. When Mercury passes through trails of comet dust, short bursts in exosphere density appear, an airless meteor shower you only detect with instruments. The 3-to-2 spin orbit rhythm leaves its mark too. Along the dawn line, the first sunlight after the long night releases more atoms, raising the exosphere there. Mercury's magnetic field also shapes this thin envelope. The field is weak, but enough to carve a small magnetosphere in the solar wind. Where that shield narrows near polar cusps, charged particles funnel down and hit the surface, freeing atoms that jump into space and feed the exosphere locally. Electric currents driven by the solar wind move charged dust and ions, shifting where material lands again. Sun to surface, surface to space, and back to surface. A quiet loop runs all the time. Why no thick air like Earth or Venus? Mass, heat, and distance set the limits. Mercury's gravity is weak, so light gases escape easily. The surface bakes for weeks, giving atoms extra speed to leave. The planet orbits inside the full glare of solar ultraviolet and the constant stream of the solar wind, both of which split molecules and kick atoms free. If early Mercury ever held more gas, the sun and low gravity made a fast pair of thief and open door. Over time, gas is left. What remains is a near vacuum in constant turnover. That absence changes how the world looks and feels. The sky is black at noon because nothing scatters blue light. Shadows are razor sharp. Heat does not move by convection, so no breezes spread it around. A sunlit patch can be scorching, while a nearby shadow is deeply cold. There are no clouds, no haze. You can see as far as the land allows. A falling rock raises dust that travels in clean parabolas and lands with no sound. Space weathering takes over the role of slow change. Sunlight, the solar wind, and tiny impacts alter colors and chemistry grain by grain. Sodium and potassium drift as single atoms, then escape or fall elsewhere. Calcium flashes off during micrometeoroid hits in hot, brief clouds. Hydrogen and helium ping off the ground like hail on metal. Each act is tiny. Over ages, the total becomes the patina we map from orbit. There can even be a faint glow from returning atoms emitting light at specific colors, though the sun's glare hides it from human eyes. Instruments tease it out to make maps. Those maps show dawnside boosts, polar cusp hotspots, and links to cold traps where water ice hides in shadow. For engineers, the lack of air is both obstacle and help. There is no air to breathe and no shield from radiation, so habitats need full life support and thick protection. There is no drag to slow a lander, so rockets must handle everything. Yet there is no weather to bury solar panels, no storms to sandblast mirrors, no humid air to corrode joints. Radiators can use the vacuum. Power lines run under a clear sky. Near the poles, the scarcity of air helps cold traps stay cold because nothing carries warmth to them. The sodium tail, fragile as it is, makes the setup feel real. You can point a telescope with a sodium filter and see a yellow fan streaming from an entire planet, renewed by sunlight, heat, and the solar wind. Atmospheres come in a spectrum from thick to almost nothing. Mercury sits near the thin end, where motion is legible one atom at a time. Silence on Mercury is not empty time. It is clean physics. Light travels straight. Landscapes keep their lines. Time stretches into long dawns and long dusks. The exosphere thins and rebuilds with the Sunday. The sodium tail waxes and wanes with the orbit. The same quiet holds when you look inside. If you could slice Mercury, you would see mostly metal with a thin, rocky rind. The planet's radius is just under 2,500 kilometers. The core likely spans about 4/5 of that distance. By mass, roughly 2/3 to 3/4 is metal. Earth has a large core, but still a thick, rocky mantle. Mercury flips that pattern, a compact world wrapped around a giant metal heart. We infer this from several lines of evidence. Mercury's bulk density is high, over 5 grams per cubic centimeter. Smaller planets are less compressed by gravity, so after you correct for that, Mercury still looks unusually dense. The way the planet spins and wobbles provides another clue. Careful tracking of rotation and tides yields the moment of inertia, which tells how mass is spread inside. Mercury's value points to mass packed deep. How the shape flexes under the sun's pull, described by a number called the love number, shows that at least part of the core remains liquid. The likely structure is layered: a solid inner core, a liquid outer core, possibly a thin, dense layer, rich in sulfur at the core mantle boundary, then a relatively small mantle, and crust above. How did so much metal end up there? Several ideas share the load. A giant impact could have stripped away rock from a larger, Earth-like proto-Mercury, leaving a core-heavy remnant. But Mercury's surface still contains more sulfur and other volatile elements than that simple picture would expect. If impact sculpting happened, it likely involved glancing, hit-and-run events and fast removal of debris before it fell back, with enough gentle handling to keep some volatiles. Another idea shifts the cause to the young Sunday close to the star. Early temperatures in the solar nebula may have allowed metal grains to condense and gather more readily than silicate grains. Radiation pressure and magnetic forces might have sorted particles by size and type, feeding more metal to the innermost bodies. This fits the general trend of compositions with distance, but again must match the volatile measurements. A hybrid story is reasonable. Start metal-favored, then trim rock by a series of impacts, while the young sun clears loose material. You end with a small world where the center really does rule. Such a core changes the planet's later life. Metal conducts heat well and cools slowly. Even for a small world, this helps keep part of the core liquid for billions of years, supported by heat from radioactive elements. A moving, conducting liquid is the key for a dynamo, the process that generates a magnetic field. Mercury's field is weak compared to Earth's, but global. Its presence means liquid metal still circulates. The large core also explains the long, curving cliffs on the surface. As the interior cooled, it contracted. Rock cannot stretch to fit a shrinking inside. It must break and slide. The result is global shortening. Lobate scarps those low, sweeping cliffs, step the ground down by hundreds of meters. They are the outer record of an inner change. Mercury's mantle is thin and likely grew stiff early. That does not mean it was always calm. The planet's smooth plains, the broad sheets that fill lowlands and basins, show that magma once reached the surface and spread widely. Many of these volcanic floods are especially clear inside big impact basins. Over time, volcanism waned. Energy turned inward. The scarp network became the main sign of change. Surface chemistry supports a deep story. Mercury's crust is rich in sulfur and other elements that favor reducing conditions with little free oxygen. That suggests an interior where iron bonded readily with sulfur and where iron in silicate minerals took a lower oxygen form. Some models include a thin iron sulfide layer at the base of the mantle, a dense lid between rock and liquid metal. Such a layer would affect how heat escapes and how the dynamo behaves. The same chemistry may help explain Hollow's fresh-looking, shallow pits surrounded by bright material. In hollows, minerals with volatile parts likely lose those parts to space under strong sunlight and solar wind, leaving Swiss cheese textures. A world-born metal-rich and oxygen-poor makes minerals that can vanish grain by grain when exposed. A metal-heavy world is not dull. Metal gives memory. Slow cooling keeps the dynamo running. The field shapes a small magnetosphere that channels particles toward polar cusps and drives currents that touch the surface. Interior contraction writes scarps that cross plains and craters alike. Even impacts may send waves through a metal-rich interior in slightly different ways than through rockier planets, helping to explain the strong, weird terrain. Opposite the Calorus Basin, where focused waves likely shattered the crust. The core's size and state are not just abstract values. They set how the planet responds to tides, how it loses heat, and how long the field lasts. They help explain why Mercury both shrank and kept a weak magnetic hum. The boundary that matters most is one you never see. The core mantle boundary deep below, where liquid metal touches rock. Above, a thin shell keeps the marks of impacts and the curves of contraction. Below, a dense ocean of iron alloy turns slowly and drives a field. A metal-rich Mercury also shows that formation close to the Sun followed different rules than Earth's. The early solar system did not mix perfectly. Distance, temperature, magnetic fields, and collisions sorted materials. One outcome was Earth, with oceans and a thick mantle. Another was Mercury, a dark stone wrapped around a bright core. Both grew from the same disk of dust and gas. Clues about the field came from spacecraft. When Mariner 10 flew past in the 1,970 seconds, the plan was to photograph the surface and sample the environment. As the probe crossed the dayside and entered the planet's shadow, its magnetometers recorded a pattern best explained by a planetary magnetic field rather than a gust of solar wind or an instrument glitch. Silence on Mercury is not only quiet, it is the outcome of physics. There is no air to carry sound, no wind to shake pebbles, no thunder to roll across crater walls. Above the ground is not a true atmosphere but an exosphere, a gas so thin that its atoms almost never collide. Each particle travels alone, leaps in a long arc, and then either falls back or escapes into space. A bottle filled with a cubic meter of Mercury's air would hold fewer atoms than a high-grade laboratory vacuum. Space begins a short step above your head. This exosphere is renewed and removed all the time. Sunlight, heat, the solar wind, and tiny impacts knock atoms loose from the topmost grains of rock. Three steady processes dominate. Photon-stimulated desorption. Light kicks loosely bound atoms off the surface. Thermal desorption. Heat during the long day bakes atoms free. Sputtering. Fast charged particles from the solar wind slam into the ground and blast atoms out. like microscopic sand blasting. Micrometeoroids add bursts by vaporizing a dusting of soil and lofting a brief plume. These are sources and sinks, not weather. The result is a moving, fragile fringe. Which atoms take part? Sodium and potassium are common, with calcium and magnesium also present. Hydrogen and helium show up too, mostly captured from the solar wind rather than native to the crust. Sodium is the showpiece. Sunlight excites sodium at its yellow wavelengths, and radiation pressure nudges those atoms away from the sunday. A faint sodium tail forms and can stretch millions of miles behind Mercury. It does not appear in normal views, but with narrow filters on small telescopes, observers on Earth have imaged a delicate fan following the planet. The smallest world wears a ghostly streamer, its exosphere pushed downwind. Because atoms seldom collide, the exosphere has rhythms set by geometry, not weather. Near perihelion, sunlight is stronger. The surface runs hotter, and sputtering can intensify in some regions. The sodium cloud thickens, and the tail brightens. When Mercury crosses a trail of comet dust, short surges in exosphere density appear an airless meteor shower that instruments can detect. The 3-to-2 spin-orbit pattern leaves a mark as well. Along the dawn line, surfaces that have spent weeks in darkness see their first light and release atoms in a short-lived boost. The exosphere also couples to magnetism. Mercury's magnetic field is weak but real and shapes a small magnetosphere in the solar wind, where that shield narrows near polar cusps. Charged particles funnel down and hammer the surface, freeing atoms that rise into ballistic paths and feed the exosphere locally. Electric currents in the magnetosphere move charged dust and ions, shifting where material lands again. Sun to surface, surface to space, and back to surface is a quiet loop that never stops. Why no thick air like Earth's or Venus's? Size, heat, and distance write the rules. Mercury's gravity is modest, so light gases reach escape speed easily. The surface bakes for weeks, giving atoms enough energy to leave. The planet orbits in strong ultraviolet light and a constant plasma stream. UV splits molecules. The solar wind knocks atoms free. If early Mercury once had more gas, the sun and low gravity made a quick path to loss. Over time, the gas is left. What remains is a near vacuum in continual turnover. That absence shapes every view. The sky is black at noon because there is nothing to scatter blue light. Shadows have knife-sharp edges. Heat does not move by convection. There are no breezes to spread it. A sunny patch can be blistering, while a nearby shadow is bitter cold. No clouds paint the horizon. Sightlines run as far as the land allows. Falling dust follows clean parabolas and lands without a sound. Slow change comes from space weathering. Sunlight, the solar wind, and tiny impacts alter surface grains and their chemistry. Sodium and potassium are knocked free and drift as single atoms. Calcium flashes off during micrometeoroid hits in hot, brief clouds. Hydrogen and helium strike and bounce like hail on steel. Each event is tiny, but over ages, they build the patina we map from orbit. There can even be a faint glow from atoms returning to the surface and emitting light at specific colors. Though the sun's brightness hides it from human eyes, instruments tease it out to make maps of source and sink. Those maps show dawnside enhancements, polar cusp hotspots, and links to cold traps where water ice hides under dark lids. It is meteorology stripped to its basics. No pressure fronts, no humidity, only production and loss. For engineering, The lack of air is both hurdle and help. There is no air to breathe and no blanket against radiation, so habitats must supply pressure and shielding. There is no drag to slow landers, so rockets must handle descent completely. Yet there is no weather to bury panels or scour mirrors, and no moisture to corrode fittings. In a vacuum, heat moves mainly by radiation, so radiators can be tuned precisely. Geometry sets power and temperature far more than day-to-day variance. Near the poles, the quiet exosphere helps permanent shadows stay cold because nothing carries warmth into them. The sodium tail offers a human-scale link to these ideas. With a sodium filter, you can watch a thin fan stream from a whole planet, renewed by light, heat, and the solar wind. Atmospheres form a spectrum, from dense to almost nothing. Mercury sits near the sparse end, where motion is visible one atom at a time. The quiet also extends inward. If you could slice Mercury, you would see mostly metal with a thin, rocky rind. The planet's radius is just under 2,500 kilometers. The core likely spans roughly 4/5 of that distance. By mass, about 2/3 to 3/4 is metal. Earth has a big core, but still a thick mantle. Mercury flips that pattern. A compact world wrapped around a large metal heart. We infer this structure from several clues. Mercury's bulk density is high, over 5 grams per cubic centimeter. Smaller planets are less compressed by their own gravity, so after correcting for compression, Mercury is still unusually dense. The way the planet spins and wobbles offers another line of evidence. Tracking tiny changes in rotation and tidal response gives a moment of inertia, a number that tells how mass is distributed. Mercury's value points to mass packed deep. How the planet flexes under the sun's pull is described by a love number. The measured response shows that at least part of the core is liquid. Put together, the picture is layered. A solid inner core, a liquid outer core, perhaps a thin, dense layer rich in sulfur at the boundary, then a relatively small mantle and crust above. How did a world end up so metal-rich? A few ideas share the load. A giant impact could have struck an earlier, more Earth-like Mercury and stripped away much of its rock, leaving a core-heavy remnant. This works for metal, but measurements from orbit also found more sulfur and other volatile elements than that simple picture might allow. If an impact sculpted Mercury, it likely involved glancing, hit-and-run collisions that removed mantle efficiently while letting some volatiles survive, with debris cleared quickly by the young Sunday. Another idea looks at the protoplanetary disk. Close to the young sun, temperatures may have favored metal grains to condense and stick more readily than silicate grains. Radiation pressure and magnetic forces might have sorted particles by type and size, feeding a metal-rich diet to the innermost bodies. This matches broad gradients in composition across the solar system, but must also match the volatile inventory seen by spacecraft. A hybrid path is plausible. A disk that already favors metal, then a series of trimming impacts. While early solar activity clears light debris, the outcome is a small world where the center matters most. Such a core sets the cadence for the rest of the story. Metal conducts heat well and cools slowly. Even for a small planet that allows part of the core to stay liquid for billions of years, supported by heat from radioactive decay. A moving, electrically conducting liquid powers a dynamo, the process that generates a magnetic field. Mercury's field is weak compared with Earth's, yet it is global. Its existence says liquid metal still circulates at depth. The large core, also helps explain the surface's long, curving cliffs. As the interior cooled, it shrank. Rock cannot stretch to fit a smaller inside. It must break and overlap. Global shortening creates lobate scarps, sweeping thrust faults that step the ground down by hundreds of meters. They are the outer record of an inner change. Mercury's mantle is thin, probably only a few hundred kilometers thick, and likely stiffened early. That does not mean the planet was always quiet. Broad, smooth plains, sheets of once molten rock that fill lowlands and basins, show that magma once reached the surface widely, especially inside large impact basins. Over time, volcanism waned, and the energy budget turned inward. Contraction and settling took the lead. Surface chemistry echoes interior conditions. Mercury's crust is rich in sulfur and other elements that favor reducing conditions, with little free oxygen. That fingerprint suggests an interior different from Earth's, with iron bonding to sulfur in the core and iron in silicate minerals taking on lower oxygen forms. Some models include a thin iron sulfide layer at the base of the mantle, a dense lid that affects how heat escapes and how the dynamo behaves. The same chemistry may help explain Hollow's fresh-looking, shallow, rimless pits surrounded by bright material. In Hollows, minerals with volatile parts lose those parts to space under strong sunlight and the solar wind, leaving Swiss cheese textures. A world-born metal-rich and oxygen-poor makes minerals that can vanish grain by grain when exposed. A metal-heavy Mercury is not dull. Slow cooling keeps the dynamo alive. The field shapes a compact magnetosphere that channels particles toward polar cusps and drives currents that touch the surface. Interior contraction writes scarps across plains and craters alike. Even impacts may send waves through a metal-rich interior in slightly different ways than through rockier worlds, which may help explain the strong, weird terrain opposite the Calorus Basin, where focused waves likely shattered the crust. The core's size and state, control tides, heat loss, and field lifetime. They help explain why Mercury both shrank and still hums weakly with magnetism. These ideas moved from guess to measurement with spacecraft. Planning for Mariner 10 focused on photography and the space environment during its flybys in the 1,970 seconds as the probe crossed the dayside and slipped into the planet's shadow. Its magnetometers recorded a pattern best explained by a planetary magnetic field rather than a gust of solar wind or an instrument error. Volcanic activity on Mercury was never about tall cones and long eruptions that climbed toward the sky. It was about broad sheets that filled lows and smoothed older scars. After the largest impacts, the mantle could still send out magma. It spread as flood lavas, cooled, and left clean edges and shallow fronts. Later, sunlight and charged particles worked on certain minerals near the surface. In places, the result is hollows, shallow, rimless pits with bright surroundings, evidence that the crust still changes where volatile bearing rocks are exposed. As the interior cooled further, the last lavas stiffened. Lobate scarps lengthened and crossed old features. The planet returned to a mostly gray surface that keeps its record for as long as light and shadow can show it. Our first close look came on a tight schedule. In the 1,970 seconds, Mariner 10 used gravity assists first from Venus, then from Mercury itself to set up 3 fast flybys. That navigation trick turned a brief visit into a sequence. March 1974, September 1974, March 1974, 975. Instruments woke for a few hours each time, recorded, and then the spacecraft slipped back into glare. The images showed a surface that looked, at first glance, like an older, denser version of the Moon. Many craters, ringed basins, bright rays from fresh impacts, and wide, smooth expanses. Mixed into that view were long, curving cliffs, lobate scarps, hundreds of kilometers long, with rounded backs and steep faces. They cut across craters and plains without regard for age. Their geometry pointed to global contraction. The outer shell had shortened as the interior cooled. Mariner 10 also carried magnetometers. As the probe crossed day into night, the field readings settled into a pattern best explained by a global dipole magnetic field, weak but organized. That result pushed back against the idea that small rocky worlds cool quickly and fall silent inside. A liquid outer core was likely still moving. The spacecraft's geometry meant that the same hemisphere had good lighting on each pass, so the mission mapped about half the planet in detail, while the other half remained unknown. Even so, it traced intercrater plains roughened by impacts, smooth plains that looked like lava floods, and the rim and exterior textures of a very large basin caloris, whose full plan would come later. Outside the basin, long ridges and grooves aligned like ripples showed ejecta that had settled in patterns set by the impact. A UV spectrometer measured the near vacuum around Mercury and found helium and hydrogen showing an exosphere that is constantly supplied and removed. At that time, the sodium tail had not yet been imaged from Earth, but the seed was planted. Mercury's atmosphere is a process atoms set free and lost rather than a weather system. The first maps answered some questions and created new ones. How widespread were the smooth plains? Were they mainly volcanic or mostly impact melt? How many scarps exist, and when did they form? Was the magnetic field a fading trace or an active dynamo? The mission left precise questions that needed a new approach. For decades after 1975, Mercury was again a bright point low in the sky. Ground-based radar hinted at bright reflections in polar craters consistent with ice in permanent shadow. Narrowband imaging found a faint sodium tail. Meanwhile, models explored how a small planet could keep liquid metal moving, perhaps with sulfur lowering the core's melting point, perhaps with uneven heat loss through a thin mantle. Messenger launched in 2004 to turn those questions into measurements. Reaching Mercury requires shedding speed, so the spacecraft took a patient path. 1 Earth flyby, 2 of Venus, then 3 of Mercury to adjust the trajectory. Each Mercury flyby in 2008 and 2009 added slices of the unmapped hemisphere. In 2011, Messenger entered orbit and began years of steady work that converted a partial atlas into a globe with context. From orbit, the smooth plains showed clear signs of flood volcanism in many regions, gentle flow fronts, embayment of older hills, and elemental patterns that differed from the highlands. Messenger also found bright, cinnamon-toned deposits around small vents, consistent with explosive eruptions in the past, proof that volatile-rich magmas once reached the surface despite the lack of air. The inventory of lobate scarps grew sharply. Scarps run through old terrains and across younger plains, confirming that contraction continued late in Mercury's history. Caloris became a full case study. The interior is partly covered by younger lava. The rim shows terraces. Beyond the rim, lineated terrain extends for hundreds of kilometers. At the antipode, the weird terrain is a field of tilted blocks and twisting valleys. likely formed where deep shock waves from the calorous impact focused and fractured the crust. These paired features tied impact physics to global effects. Tracking the spacecraft's radio signal allowed precise gravity mapping. Those data, combined with observations of tides and spin, sharpened the picture of a very large, partly liquid core under a thin mantle and crust. Magnetometer results showed a global dipole offset northward from the planet's center, a clue to asymmetry in the core or in heat flow at the core mantle boundary. A laser altimeter mapped topography in detail, especially in the polar regions, and a neutron spectrometer detected hydrogen. Together with Earth-based radar, those measurements confirmed water ice in permanently shadowed craters near both poles. In some places, bright, clean ice lies at or near the surface. In others, a dark, insulating layer a few decimeters thick covers brighter ice below. Messenger also recorded features not expected before arrival. Hollows, those shallow, rimless pits with bright halos dot crater floors and plains. They likely form as volatile-bearing minerals lose components to space under strong sunlight and solar wind, leaving soft, easily removed material behind. Hollows cut both old and younger surfaces, which means the process is still active at a small scale. Mercury is not static. It changes in fine detail, where chemistry and radiation allow. By the end of its mission in 2015, when the spacecraft impacted the surface after running out of propellant, Mercury had moved from a half-seen object to a well-characterized world. The step was not just better images, it was a deeper understanding. Mariner 10 showed contraction and magnetism. Messenger quantified contraction, mapped scarps across ages, identified volcanic plains and explosive deposits, confirmed polar ice, outlined a core that remains partly liquid, and revealed a magnetic field with a clear offset. Gaps from the first mission's lighting constraints were filled with global coverage and precise topography. Patterns that once looked like guesses became measured links: impact to ejector, to lava, to fault, with relative ages set by cross-cutting traces and absolute ages anchored by crater counts and composition. The mission design itself added method to the science. Gravity assists conserved fuel and made a tough target reachable. Repeated flybys previewed the unknown hemisphere and refined navigation. Long orbital campaigns allowed mapping under many sun angles, so relief and composition could be separated cleanly. Instruments overlapped by design cameras with color filters, X-ray and gamma-ray spectrometers, a laser altimeter, magnetometers, a neutron spectrometer, and precise radio tracking so that single results could be checked against others. The broad picture that follows from those data is consistent and specific. Mercury's surface shows both very old intercrater plains and younger smooth plains formed by volcanism. Lobate scarps record global shortening driven by interior cooling. Caloris and its antipode tie local impact to planet-scale effects. Polar craters trap water ice in permanent shadow. The core occupies most of the radius. Part of it remains liquid and powers a global magnetic field that is offset northward. The exosphere is renewed by sunlight, heat, the solar wind, and micrometeoroids, and it includes a sodium tail seen from Earth with narrow filters. Hollows point to near-surface minerals that lose volatile parts under radiation and heat. After Messenger, questions grew more focused. How the dynamo operates in such a small world, how heat leaves the core through a thin mantle, why the magnetic dipole is offset, how often explosive volcanism occurred, how hollows evolve, and how the exosphere responds to solar activity over time. Those are the kinds of questions that ask for a new platform with different instruments and a long, calm view. A mission like this asks for two kinds of eyes. One must fly close to the ground and trace the surface, the gravity, and the thin veil of atoms around the planet. The other must watch the larger space, where the solar wind meets a small magnetic bubble and field lines stretch into a tail. That is why the stack separates at Mercury. Europe's orbiter will take a low, tight path to map the planet itself. Japan's orbiter, Mio, will fly higher and wider to study the magnetosphere, the exosphere, and the solar wind around them both. The low orbiter carries cameras for detailed imaging, a laser altimeter to measure height, spectrometers to read chemistry, and a thermal mapper to track how the ground heats and cools. With repeated passes under different lighting, it will extend a global topographic map and refine boundaries between old intercrater plains and younger smooth plains. It will look again at volcanic fronts, at the subtle rims of buried craters, and at the long arcs of lobate scarps that step the terrain down by hundreds of meters. Its spectrometers will separate rock types and quantify elements, testing how widespread the oddly low iron and high sulfur signatures are, and checking the patches of low reflectance material that likely include carbon. A radio science package will time signals with great precision to weigh mountain belts and basins and to read tiny tides raised by the sun, which together sharpen the size and state of the core. Mio's job is the broader environment. It carries magnetometers to trace changes in the field, particle detectors to count ions and electrons, and sensors for neutral atoms that drift off the surface. As the solar wind presses on the day side, reconnects field lines, and drives currents into polar cusps, Mio can measure the energy flow. Farther down the tail, it can catch the field stretching and snapping in small substorms and see how fast material escapes. With two spacecraft working together, cause and effect become clearer. A burst of charged particles seen by Mio can be tied to a patch of surface atoms seen by the low orbiter, or to a change in the sodium tail imaged in a narrow color band. The pairing turns snapshots into sequences. Thermal control is a quiet challenge. Close to the sun, sunlight is intense and long. The low orbiter must keep its instruments in a safe temperature range, while it looks at a surface that swings between extreme heat and extreme cold. Radiators, reflective coverings, and careful pointing share the work. Long eclipses hide the sun and drop the temperature. Long days do the opposite. The crew stack's sunshield protected Mio en route. After separation, its own design must handle both heat and shadow. Solar panels feed the power budget, but their angle is a constant trade between energy and temperature. Mapping the magnetic field from a low path matters because Mercury's dipole is offset northward. The low orbiter will fly over all latitudes and longitudes and gather enough crossings to place that offset more precisely and to track changes with time. If the field drifts or breathes with the solar cycle, a long dataset will show it. Mio's high passes will catch the magnetopause, the boundary where the solar wind meets the field, at many angles and pressures. Together, the data can test whether the offset comes from how heat escapes the core, from a stable layer above the dynamo that muffles southern flux, or from some mix of both. The exosphere needs repetition. Atoms are knocked off by light, by heat, by sputtering, and by small impacts. The supply rises near perihelion, during micrometeoroid streams, and at dawn. The low orbiter can measure sodium, potassium, calcium, and magnesium close to the planet. MEO can sample the plasma that helps free them and steer them. When the sodium tail brightens in a narrow-band image, particle sensors can report whether a dust stream or a solar wind pulse was the trigger. Over many Mercury years, patterns will emerge, regular boosts tied to orbital position, and irregular ones tied to external events. Polar craters remain a special target. The laser altimeter on the low orbiter can refine models of which floors are truly sunless and by how much. Neutron and gamma-ray spectrometers can test how the hydrogen signal varies across shadows and how deep the bright, clean ice extends. A thermal imager can map how steeply temperatures fall just inside the shadow line and how a thin, dark cap, likely made of radiation-cooked organics, insulates the ice below. Small changes after a micrometeoroid surge can be checked for fresh exposure or burial. Surface processes that act slowly can be caught by patient imaging. Hollows appear as fresh, bright patches around shallow pits. By revisiting hollow fields under the same lighting, the low orbiter can look for growth at the edges or for new pits where volatile-bearing rocks have been exposed. Wrinkle ridges and small scarps can be measured for crispness and offset to test how late contraction continued. The straight edges of some scarps and the way they slice through rims help fix the order of events in crowded terrains. With global coverage, the story can be mapped beyond Calorus to other basins and plains that were only lightly sampled before. Radio tracking is another quiet tool. As the spacecraft passes behind Mercury from Earth's point of view, radio signals skim the exosphere and can be delayed or shifted subtly by the thin gas. Those changes add information about density and composition. The same radio system measures gravity by timing every tiny Doppler shift due to hills, basins, and tides. Over time, the pattern of tidal flexing can refine the planet's love numbers and help pin down the size of the solid inner core and the depth and composition of the liquid outer core. Thermal mapping across many local times will give a fuller view of how different materials store and release heat. Fine dust and rock slabs behave differently. Areas with more fractured rock or thicker regolith cool faster at night and heat faster in the morning. Knowing those properties helps separate composition effects from texture effects in color images and ties optical units to physical ground conditions. It also sets practical bounds for future hardware that must endure long, slow noons and long, slow nights. The long cruise, with many flybys, has already provided side benefits. Each Mercury pass added coverage of high latitudes and parts of the far side that earlier missions missed. Low-angle sunlight emphasized relief along scarps and rim fragments. The gravity field was sharpened by minute bends in the flight path. Those incremental gains make the start of orbital science more efficient because maps and models are already primed. Mercury's interior remains the central puzzle that everything else touches. A large core with a likely solid inner part and a liquid outer part sets the planet's rotation, tides, and field. If the inner core is growing as the planet cools, that growth releases heat and light elements into the outer core, which can buoy and drive the dynamo. If a sulfur-rich layer sits at the top of the core, it could slow mixing and shift where flux emerges. Surface data offset fields, contraction amounts, chemical maps are the clues. The low orbiter will watch the surface. MEO will watch the field and the plasma. The fit between the two will test how the dynamo works in a small world. Composition maps should tighten the picture of a reducing planet. High sulfur and low iron in surface rocks point back to an early environment with little oxygen available. Differences in magnesium, calcium, aluminum, and potassium across units can tell whether smooth plains share a source or if multiple magma batches rose at different times. Low reflectance material, likely rich in carbon, can be traced to see whether it caps old units, lines crater walls, or sits as reworked debris. Those patterns help decide between a primordial, graphite-rich crust floated on an early magma ocean and alternative sources. Mio's high orbit will catch how the magnetotail forms and releases energy. Small substorms can be timed against bursts in the exosphere and against changes on the surface where cusp precipitation frees atoms. The dayside boundary's position, shape, and roughness as the solar wind varies will test how a small magnetosphere scales from Earth-sized behavior. Near Mercury, the bow shock can sit close to the surface. Reconnection there can be rapid, letting solar wind plasma reach the ground and sputter material directly. Measuring those episodes tells how often surface atoms feed the exosphere and how quickly they escape. At lower altitudes, the low orbiter can watch aurora-like emissions on the night side in ultraviolet and X-ray bands caused by particle impacts in the exosphere. It can tie those glows to Mio's measurements of particle populations and to changes in magnetic topology. It can also look for heat anomalies that might mark rock types with different thermal inertia, or for subtle elevation changes that tie to buried ring structures from old basins. Engineering choices also turn into science returns. The ion thrusters that push the stack inward use xenon ions accelerated by electric fields. Their long, gentle thrusts carry the stack through arcs where sunlight, angles, and temperatures vary in planned ways. Each geometry provides a different look at the planet's reflected and emitted light, which helps calibrate instruments before orbital work. The timing of flybys can be set to catch Mercury near perihelion or aphelion, giving natural experiments on exosphere response to changing distance from the Sunday. Working near the Sun forces clean scheduling. Communications windows must avoid pointing radiators at hot directions. Instruments that heat the spacecraft must share time with those that prefer cold. The result is a cadence that samples many local times and latitudes across orbits. Over months, that cadence fills in a grid, dense enough to track slow processes, the darkening of fresh rays, the brightening or retreat of hollow margins, the seasonal brightening of sodium, the steadiness of ice signals inside specific shadows. The most basic questions remain clear. How thick is the crust? And does it vary under basins compared to highlands? How much has the planet shortened since its outer shell stiffened? And did shortening come in pulses or steadily? How offset is the magnetic dipole? And does the offset drift? How do exosphere sources split among light, heat, sputtering, and impacts? And how does that split change with Mercury's orbital position? How often did explosive volcanism occur? And when did the big plains stop forming? Each answer tightens a chain from formation to present state. A world without air, without weather, and without plate tectonics records its history plainly. The new orbiters will use that clarity. One will read the ground and the thin gas close to it. The other will read the space around it. Between them is the thread that connects surface chemistry, interior cooling, magnetic fields, and the behavior of atoms at the edge of space. One family of explanations leans on the early solar nebula. Very close to the young sun, temperatures and radiation may have favored metal grains condensing and clumping more readily than silicate grains. In that environment, small building blocks that fed inner planets could have been metal-rich from the start. Sunlight and magnetic fields may also have sorted particles by size and type, nudging iron grains inward faster than rocky dust? If so, Mercury accreted from feedstock that already tilted toward iron. Another family of ideas puts more weight on collisions. Early in solar system history, many growing worlds crossed paths. A glancing, high-speed hit-and-run impact can strip away part of a planet's rocky mantle more efficiently than its dense core. If such events happened more than once, a proto-Mercury could have lost a large share of its silicates while keeping much of its metal. The debris might then be swept inward by the young sun's radiation or scattered away by later encounters, leaving a compact, core-heavy remnant. The chemistry we see at the surface, rich in sulfur and other volatile elements, argues against a single, fully vaporizing blow. It fits better with a sequence of partial removals and quick cleanup by solar forces, plus original material that was already formed under reducing conditions with little free oxygen. A hybrid path is likely. Start with a disk region that gave inner bodies more metal. Add several grazing impacts that trimmed mantle without boiling everything off. Let early solar wind and light pressure help carry away the loose rock fragments before they fell back. The result is a small planet whose inner makeup matters more than usual, and whose thin mantle cooled quickly into stiffness. That anatomy shaped every later chapter. A large metal core conducts heat well and cools slowly, even in a small world that can leave a liquid outer layer for billions of years. A moving, conducting fluid is the basis for a dynamo, which matches the global magnetic field that Mariner 10 and Messenger measured and that Mio will watch in detail. The same cooling shrank the interior. Rock cannot stretch to fit a smaller inside, so the crust shortened. Lobate scarps long, curved thrust faults step the surface down by hundreds of meters, sometimes more, and cross both old and young ground. Bepi Colombo's low orbiter will map those scarps at higher precision to tell whether the last increments of shortening continued late, and by how much, in different terrains. Volcanism on Mercury flows from the same deep setup. A thin mantle does not support Earth-style plate tectonics, but it did allow early flood lavas to spread widely, especially inside big basins where fractures opened pathways. Compositions measured from orbit show iron-poor, sulfur-rich lavas, consistent with melts tapped from a reducing interior. Explosive deposits around small vents prove that some magmas carried gases even without an atmosphere to hold a plume. Bepi Colombo will check whether smooth plains in different basins share chemistry, or point to separate magma batches that rose at different times. Surface chemistry also ties to odd, small-scale features. Hollows bright-rimmed. Shallow pits tend to form where volatile-bearing minerals at the surface lose their volatile parts to space under strong sunlight and solar wind. The result is a fragile texture that collapses into pits. By revisiting hollow fields, the low orbiter can look for changes at the edges or for new pits, testing whether the process continues under present conditions and whether it depends more on local composition or on exposure history. Mercury's exosphere connects the surface to space, one atom at a time. Sodium and potassium atoms are knocked loose by photons, heat, and sputtering. Radiation pressure pushes sodium into a faint tail. Mio's particle detectors will catch the solar wind streams and reconnection bursts that open the way for charged particles to hit the surface near polar cusps. The low orbiter's cameras and spectrometers can watch how sodium and other species brighten at dawn after the long night, and how they respond during micrometeoroid showers. Coordination between the two spacecraft should reveal whether spikes in the tail line up with bursts of particle precipitation, with Mercury's distance from the Sun, or with dust streams in its path. At the poles, permanently shadowed craters act as freezers. Radar from Earth and instruments on Messenger show bright, hydrogen-rich deposits consistent with water ice, sometimes clean at the surface, sometimes buried under a thin, dark lid that insulates against stray warmth. The laser altimeter and neutron, gamma-ray sensors on the low orbiter will refine which floors are truly sunless and how the hydrogen signal varies across shadows and rims. MEO's high-latitude passes will sample the particle environment that may add or remove surface material there. The combined datasets should trace how water arrives by comets, by certain asteroids, and by slow release from minerals, and how it migrates into the coldest traps. Mercury's magnetosphere scales down Earth's system into a compact, more direct version. The bow shock can sit close to the surface. Reconnection on the day side can be rapid, letting solar wind plasma reach the ground in bursts that sputter atoms and feed the exosphere. The magnetic tail stretches and snaps in small substorms. MEO will measure those fields and particles at many local times. The low orbiter can look for UV and X-ray emissions on the night side, where particles hit the thin gas, and for surface changes in cusp regions after strong events. That pairing will test how a weak dynamo behaves so near the Sun and how external pressure reshapes it. Radio science will continue to pull on the interior thread. As the spacecraft circle Mercury, tiny Doppler shifts in their radio links measure gravity variations from mountains, basins, and density contrasts at depth. Over months, the pattern of solar tides will refine Mercury's love numbers values that reveal how easily the body deforms and sharpen estimates of solid inner core size and liquid outer core depth. If a sulfur-rich layer sits at the top of the core, it could change how the field emerges and why the dipole is offset northward. Repeated passes will help distinguish that scenario from others. Thermal mapping under many sun angles will separate material properties from composition. Fine dust and massive blocks store and release heat differently. Planes with thicker regolith cool faster at night. Rockier units lag. Those differences help interpret color mosaics and decide where chemistry, rather than texture, is responsible for a unit's tone. They also set design bounds for any future landers or instruments that must endure long, slow noons and equally long, slow nights. The comparative angle remains useful. The Moon is a rocky shell with a modest core, fewer and smaller scarps, and basalt seas that reflect local mantle melts. Mercury is metal-dominated, with planet-spanning scarps and sulfur-rich lavas. Venus is Earth-sized, yet lacks a global magnetic field, despite its mass. Mercury is small, yet keeps one. Those pairings test dynamo theory. Size helps, but composition, cooling paths, and boundary layers set the rule. Earth's plate tectonics cools its core efficiently. Mercury's thin mantle cools in a different pattern, and a stable layer above the dynamo may shape where and how flux escapes, which could explain the northward offset. Mercury also remains a clean test of gravity. Its elliptical orbit precesses faster than Newtonian calculations with planetary tugs can explain by a small but measurable amount. General relativity accounts for the extra 43 arcseconds per century near the Sunday modern. Tracking folds that correction into navigation and radio ranging as a matter of routine. As Bepi Colombo logs long stretches of precise tracking near perihelion and aphelion, the data can help bound any tiny deviations that future theories might predict, using the smallest planet as a probe in a strong field region. Ground observers still have a role. From Earth, Narrowband sodium images can follow the tail's brightness over Mercury's 88-day year and during known micrometeoroid streams. Those time series can be compared with the spacecraft's in-situ particle counts and exospheric measurements. Transits across the Sun, rare but predictable, remain chances to tighten orbits, check instrument calibrations, and engage a broader community in careful observation. Greatest elongations, when Mercury is farthest from the Sun in the sky, are still the best times for small telescopes to catch phases and changes in apparent size. Those simple observations fold into a larger pattern of professional and amateur data that has been useful for decades. The open questions are specific. How large is the solid inner core, and is it growing fast enough to drive the dynamo by releasing light elements into the outer core? How thick is any stratified layer at the top of the core? And how does it shape flux so that the dipole is offset north? Did contraction proceed in pulses tied to interior milestones, or as a slow, steady squeeze? Are smooth planes in different basins made from the same melt families, or do they point to distinct sources and times? How quickly do hollows expand today under current sunlight and solar wind? How often do cusp events loft fresh sodium compared with micrometeoroid surges? Answers will come from overlap. Two orbiters watching the same system from different heights. Ground telescopes watching the tail, and models tying the pieces together. Mercury rewards that approach because it keeps records well. Without air and without plates, the surface holds lines in place for long spans. With a big core and a weak but global field, the interior stays active enough to leave signals in the magnetosphere and in slow tectonics. With cold traps and a thin exosphere, atoms move in ways that reveal sources and sinks cleanly. The smallest planet remains a direct one to study. Its light is strong when geometry is kind, its scars are readable when the sun is low, and its field talks in subtle shifts that good instruments can hear. The plan now is to listen long enough and at enough scales to connect the motions of liquid metal at depth to a sodium atom drifting in space a few hours after dawn. Another line of thinking leans on dynamics. A proto-Mercury could have endured one or more hit-and-run impacts that shaved off rocky mantle more readily than dense metal, leaving a compact, metal-rich remnant. Reality may be a blend, a metal-friendly birth zone, revised by violent encounters, then cleaned by the young sun's winds that swept away debris before it fell back. Whatever the exact mix, the outcome says the inner solar system did not hand out ingredients evenly. Distance mattered, chemistry mattered, timing mattered. Surface chemistry pushes the story further. Messenger's measurements showed a crust unusually rich in sulfur and other volatiles for a world baked so near the Sunday. That single fact forced origin models to keep light elements in play rather than erasing them. It points to formation. Under reducing conditions, little free oxygen so iron bonded with sulfur and carbon survived to darken some units as low reflectance material. The hollows, the bright-rimmed shallow pits where volatile-bearing minerals vanish grain by grain under fierce light, turn chemistry into sculpture. The rocks still whisper what they are made of. Mercury also revises our sense of planetary adolescence. Small, rocky worlds were once pictured as cooling quickly into silence after early bombardment. Mercury stretches that timeline. Its smooth plains record wide volcanism after the Great Basins formed. Its lobate scarps show that global contraction continued well afterward, offsetting even relatively young plains. Magnetic data say a liquid outer core remains. Together, the picture is not a sprint into stillness, but a glide, active early, then quieter, yet still humming faintly within. For rocky exoplanets close to their stars, that matters. Small and close does not always mean dead. In comparisons, Mercury is a benchmark for extremes. Shortest year, one of the longest solar days. Stark thermal contrasts, because there is no air to share heat oven in sunlight. Cryogenic a few steps into shade. A global field despite small size. Ice in polar pits, while the equator smolders. Each most tests a principle. The 3-to-2 spin-orbit resonance shows how tides on eccentric paths find unusual balance points. The exosphere's sodium tail shows how a surface can feed a collision-free atmosphere one atom at a time, and how radiation pressure shapes it. The polar cold traps show how geometry alone, low sun angles, deep rims can do the work of climate when there is no climate at all, storing water molecule by molecule in darkness older than continents. Where does that leave the start of the solar system? With a more textured story than a simple rock-to-gas gradient. Mercury's composition says the inner disk was chemically varied and dynamically busy. Its metal-heavy body says collisions near the Sun were not just common, but selective in what they removed. Its persistent dynamo says small cores can stay liquid if alloyed and cooled in the right way. Its surface says violent impacts can open paths for calm lava. Cooling can wrinkle a world into cliffs as tall as towers, and sunlight alone can etch rock without any help from wind or rain. All of that tightens the early timetable. When planetesimals formed, how fast they heated, how long magma oceans lasted, how often bodies grazed instead of merged. There is a gentler legacy in method. Mercury teaches that illumination angle is an instrument. Low sun to read relief, high sun to separate compositions, mid-sun to trace boundaries. It tells us to look in the corners, the poles where light never goes, the dawn line where the exosphere wakes. It reminds us first impressions mislead. A grey disk became a laboratory for relativity. A dead planet kept a living core. The nearest world to the sun kept ancient frost. The method is humility with persistence. Return more than once. Measure more than one way. Let small surprises add up until the picture changes. If the moon teaches endurance, Earth teaches complexity, and Venus teaches caution, Mercury teaches clarity. Without air or water to blur its lines, causes and effects sit close together. Impact and basin, basin and lava, cooling and scarp, sulfur and hollow, sunlight and ice. The planet is not simple, it is honest. From that honesty comes a legacy larger than its size. We learned that gravity bends paths measurably because Mercury's orbit was there to be measured. We learned that world-making ingredients vary with distance and history because Mercury wears its alloy on the outside. We learned that silence is not emptiness because a thin exosphere still flows, a faint field still hums, and light alone can draw a kind of weather across stone. Stand, in thought, on a lava plain under a black noon sky. The sun is large, shadows are sharp, air is absent. Around you are the results of collisions you did not witness, eruptions you did not hear, and cooling you cannot feel. Yet everything is visible and steady. That is Mercury's gift, to show without fuss how worlds become themselves. In doing so, it says something steady about our beginnings. The solar system did not debut fully ordered. It argued, collided, sorted, and cooled into shape. A small, quiet planet kept the minutes. Listen closely to Mercury, and you notice the absence of sound first. No wind in ridges, no waves on a shore, no leaves whispering. Only light moves here. It creeps and hesitates, then carries the day. In that quiet, the planet's character becomes plain. It deals in strong contrasts and simple truths. Sunlight draws hard lines. Shadow keeps its promises for centuries. It is small, but it does not fidget. It is close to the sun, but it does not boast. It keeps steady time in an orbit that loops and precesses, quick in the year, unhurried in the day, faithful to a rhythm set long ago. We have walked with it in thought. We have stood at the edge of Caloris and traced ring upon ring, echoes of a single instant that traveled around the globe and jumbled hills on the far side. We have crossed smooth plains and older pitted ground, reading age in crispness and color. We have climbed lobate scarps and felt the crust step over itself to fit a shrinking interior. We have peered into hollows where a sun too near draws secrets out of stone. We have looked toward the poles and imagined frost older than history. We have watched sunrises so patient that they redefine the word. We have also listened below. Mercury carries a deep ocean of liquid metal around a solid heart. That slow ocean writes a magnetic field into space, weak, offset, and enduring proof that motion persists below as the crust wrinkles above. Small is not simple. Near is not empty. The smallest planet can hold a dynamo. The closest planet can keep ice. An airless planet can still be busy in ways our senses must learn to see. Mercury has a way of drawing out good questions. Why 3 spins for 2 orbits? And what does that do to noon and night? How does a planet that should have cooled into silence keep a field alive? What early kitchen could bake a body so metal-rich and yet preserve sulfur and other volatiles? How does ice find shadow in a place where light is so sure of itself? Answers grew from patient instruments and the habit of returning. Mariner 10 taught us to expect surprises and value clever paths. Messenger taught us to map slowly and measure across many senses until chemistry, gravity, and magnetism agreed. Bepi Colombo is on the way to add the next lines. An essential theme has emerged. Mercury is not a footnote in other worlds' stories. It is its own text, short, dense, and worth rereading because it changes with the light. On Earth, causes and effects are braided by air, water, and life. On Mercury, much of that chatter is absent. Impact makes basin. Basin invites lava. Lava cools, and the planet tightens. Sunlight etches. Shadow preserves. The sequence is not cold. It is clear. That clarity turns out to be a gift because it lets us test how rocky worlds begin and age. We can carry those lessons back to Earth and Venus and out to rocky exoplanets circling close to other stars. To spend time with Mercury is to change your scale of patience. Our days are full of quick signals and shifting skies. Mercury asks you to imagine dawn stretched over weeks, noon that pauses, and sunset that lingers until you can feel orbital motion in your bones. It asks you to think of heat and cold as principles to see how a few steps can trade one for the other. It shows that geometry is a quiet kind of climate, no less exact for being silent. It rewards attention that takes time, low sun, long shadow, repeated passes, the pace that suits a mind easing toward rest. For all its seriousness, Mercury leaves room for gentle humor. A planet famous for speed hosts one of the longest solar days. A world next to the sun keeps ice. A body thought too small for an active heart hums with a field. An airless world wears a comet-like tail of sodium, a reminder that air can be a verb as well as a noun. These are not punchlines, only small, instructive reversals that make learning feel light. There is another feeling that grows while tracing Mercury's path: gratitude for the craft of inquiry. Trajectories borrow from gravity, like a careful dancer borrows weight from a partner. Instruments measure in colors we cannot see, and in times too brief to count. Teams work for years to assemble a mosaic, a curve on a plot, a pass in darkness that catches the rim of a crater and proves it is shadow forever. The planet is silent, but the attention brought to it is full of human effort, calculation, debate, patience, and the quiet joy when a line of data makes a mystery less so. To notice a small world, honestly, is a kind of kindness. If there is a thought to carry into sleep, it is this: even the smallest world has room for a great story, and most of that greatness is made of small, exact things: an angle of light, a fraction in a resonance, a handful of atoms leaving a surface, a cliff that drops by a clean measure where rock slid on rock. Together, they become character. Mercury is the messenger here, not because it runs fast, but because it shows how much can be said without raising a voice. So let your breath slow with its long dawn. Picture a pale plain under a black sky, the sun a little larger and a little whiter than you expect, a ribbon of cold at your feet, a scarp in the distance drawing a dark line across bright ground. Think of the deep interior, a metal ocean turning slowly enough to make magnetism out of time. Think of a polar floor, quiet enough to keep frost for ages, and a sodium tail streaming invisibly downwind, renewed each day by light alone. Consider how a small world keeps good records, and how reading them teaches us to listen better elsewhere. When you next see a tiny spark near the horizon, early or late, you will know a little more of what it is. Not just a point slipping into glare, but a patient planet that has kept time for the solar system longer than names for time existed. It circles, it turns, it draws long dawns and longer dusks, and it lets physics write simple poetry on stone. And as your eyes close, hold to a quiet confidence that the universe hides its richest stories where it looks most bare. Mercury wears one of them openly. All it asks is that you look, wait a little, and let the silence do its work.